before that, I want to introduce our speaker, Dusit Niyato. He's a professor of the School of Computer Science, Engineering at NTU. His current research are in the area of sustainability, edge intelligence, and decentralized machine learning and incentive mechanism design. He apologized he can't make it today. He got urgent thing to attend. But feel free to email him if you have any question after this talk.
Welcome to the talk, Semantic Communication with Edge Intelligence. This is by Dusit Niyato. The detail of this talk can be found in the paper Semantic Communication with Edge Intelligence, available on arXiv. Introduction. So we have wireless network, 2G, 3G, 4G. So this cellular network has been used well for the Internet of Things technology. That means the wireless system can be used to connect sensors, actuators, and other devices. Now we are working in 5G. So the things, objects, become more intelligent due to the advancement of the AI and machine learning. Therefore, we can say that 5G is the Internet of Intelligent Things. And for 6G, people envision that 6G is the wireless system that is enabled by AI. And therefore, it's not that just the things, objects and sensors that become more intelligent. The wireless network, 6G, will be intelligent as well. So we can say that 6G will support intelligent Internet of intelligent things. So the key technologies to transfer from 5G to 6G are the edge intelligence and semantic communication. So edge intelligence will focus on how to make the network edge devices become more intelligent in servicing or adapting the resource allocation, while the semantic communication will facilitate the transfer of useful information. Here from 5G to 6G, edge intelligence and semantic communication will enable many features, including computing force network, AI native network, ubiquitous connectivity, trustworthiness native network. So there will be many applications running on 6G, such as holographic telepresence, hyper-intelligence IoT, unmanned aerial vehicle, and collaborative robot or swarm intelligence. Now we look at three-level communication model. Level A, we are concerned with the question, how accurately can the symbol of communication be transmitted? This is technical problem. The next level is level B, where we try to answer the question, how precisely do the transmitted symbol convey the desired meaning? And this is the semantic problem. The next level, level C, we need to answer how effectively does the received meaning affect and conduct in the desired way. This is effectiveness problem. In the other words, it means that how can we use the information to achieve the objective or the goal of the communication, for example, to make the decision. So on the right hand side here, we have the classical communication system. We have the source encoding, channel encoding, and then the symbol will be transmitted over the physical channel, which can be interfered and tampered by physical noise. At the receiver, the channel decoding is performed, followed by the source decoding to obtain the original data. Basically, in classical communication system, it is the pursuit of replica of source data. It used the channel theory as a basis for the system design, where information is defined as what can be used to remove uncertainty. And the link capacity is based on mutual information in the entropy domain. Here, if we have the different way of increasing the network capacity, including broaden the available spectrum, stack computation modules, increase edge, access point density, increase the antenna density. However, this technique will increase the system complexity. Consider the comparison between the classical communication and semantic communication. In classical communication, we have source image. So the source image will be translated into the stream of bit, and then the transmitter performs the source encoding, channel encoding. The symbol is transmitted over the channel, and then at the receiver perform the channel decoding and source decoding to obtain the duplication of the data, which is the same original image. On the other hand, in semantic communication, the source data can be images, but the source may have the knowledge that the receiver is the autonomous car. So the source data can perform the joint semantic channel encoding by extracting the meaningful semantic information to the receiver. For example, the traffic light will be the semantic information which is useful for the vehicle. Also the car in the front and the right hand side and pedestrian will be important for the receiver. The traffic sign and the car in the front of the vehicle will be important semantic information. Here we perform the joint semantic channel encoding and then transmit the bit, the symbol of the meaningful semantic information over the wireless channel. And at the receiver will perform the joint semantic channel decoding to obtain the semantic information. So the semantic information is not the same as the raw image or raw data at the source. The semantic communication can be represented as the communication of human. For example, Paul has a mental model, would like to meet Peter. So Paul wants to meet Peter in Rome. Paul will send the message from Paul to Peter, let us meet in Rome. Here there could be the metadata where Paul indicates that Rome is a city and Rome can be identified by Wikipedia and other metadata source. Peter, once receives the message, the system will match to Peter that Rome, by using the public identifier, Peter can connect to the thought of Paul that Paul wants to meet Peter in Rome, which is a city in Italy. Okay, another example, we have the sender, which could be husband, and the receiver, which could be wife. So wife would like to know what the kid is doing. So here, if the husband knows the purpose of the receiver to communicate, the sender can extract the information for the activities of the kids riding bicycle and send that semantic information to the receiver without the other information such as the tree at the background and glasses in the front and at the back. Here, semantic communication allows the meaning of message behind the digital bit to be extracted and exploit during communication. This will significantly improve communication efficiency and support human-oriented services. So, deploying semantic communication in wireless network faces a number of technical challenges. Some of the questions include how to model the semantic information of data, how to evaluate the performance of the semantic communication, how to design a semantic-oriented resource allocation schemes and traffic scheduling to optimize the semantic information transmission. There are other questions pertaining to semantic encoding and decoding, as well as security of semantic communication. Semantic communication framework. Semantic communication model differ from traditional channel communication into the fact that it incorporates human-like understanding and inference into the encoding and decoding of communication data. We can look at the semantic information, which is based on semantic extraction by dividing into the three levels. Effectiveness level, that we consider the goal of the communication. We have the semantic level that cover the background knowledge, share knowledge, semantic representation, semantic encoding at the source, semantic channel, semantic noise that can make the transmitted semantic information ambiguous, and the semantic decoding and semantic interpretation at the receiver. And we have technical level for the wireless channel encoding, physical channel, physical noise, and channel decoding at the receiver. Here, the semantic representation module, we extract the useful semantic information and remove the irrelevant information before transmission. Semantic interpretation module infer the intended meaning of the sender or the desired action to be performed by the receiver. Background knowledge of communication parties has to be shared in real time. This is to guarantee that the processes of representation and inference of the semantic information can be well matched. Otherwise, there could be the semantic noise generated which make the meaning and usefulness of the information will be degraded. Then we have communication goal. In some cases, like multi-objective identification, the possibility for communication goal should be included in the background knowledge, and the communication goal should instruct semantic extraction method to filter out non-related semantic information transmission. This is according to the current communication goal. Therefore, in general, semantic representation, semantic interpretation, and semantic decoding need to be combined into a single module in a practical system design. In semantic communication, semantic extraction methods are important components. We can look at deep learning-based semantic extraction method that utilize convolutional neural network, transformer, attention mechanism, ResNet, generative adversarial network to obtain semantic information from the input data. This will enhance the system robustness at the low signal-to-noise ratio due to the shorter bit flow. For the deep learning-based semantic extraction, we can use the cross entropy and mean square array error in the training process. They can be the loss function that need to be differentiable. However, in some cases, we don't have the function that is differentiable. We can resort to reinforcement learning-based semantic extraction method, we can adopt the more general semantic metrics, such as blue score in the semantic extraction training process. Again, we can employ self-critique training to address the issue of identifying the intermediate reward. For the non-sequential task, the decoding process needs to be transformed into a recurrent procedure beforehand in this reinforcement learning-based semantic extraction method. Knowledge-based assisted semantic extraction method. It will integrate the knowledge base into the encoder and decoder. The purpose is to extract more relevant information for the scenarios with multiple communication tasks. Here, the knowledge base in semantic communication is composed of source information, goal of the task, and the possible ways of reasoning that can be understood and learned by all the communication parties. We can look at the semantic native, semantic extraction method. Here, the semantic information can be learned from the iterative communications between intelligent agents that represent the transmitter and receiver. This is through the contextual reasoning, which make it possible to the cases where the semantic vary over time and different contexts. In this semantic native method, communication party can be enabled with the capability of contextual reasoning to improve the communication efficiency. Next, we look at the semantic metrics. How can we evaluate whether the semantic communication is accurate and efficient or not? In classical communication, the metrics performance include bit error rate, symbol error rate, delay, throughput. Basically, they evaluate performance from the different network layers, and they treat every bit, symbol, packet as equally important. On the other hand, semantic metrics for the semantic communication performance can be based on error-based, age of information-based, or value of information-based. They measure the performance from the semantic domain. The semantic contribution of each packet is not equally important. Here, the different kind of the semantic matrix can represent the different semantic level and effective level. The error-based matrix will be more toward semantic level, while the value of information-based matrix is toward more to effectiveness level, while the age of information-based matrix is in the middle. First, we look at error-based semantic matrix. The error-based semantic matrix are concerned with whether the destination can recover equivalent meaning from the received message to that in the transmitted message. It measures the differences in the meaning conveyed by the recovered data and source data. Some of error-based semantic metrics from the natural language processing are given here. It could be bilingual evaluation under study, blue score. This blue score considers the linguistic law such that semantically consistent words usually come together in a given corpus. However, the limitation is that the blue score only calculates the differences of words between two sentences and has no insight into the meaning of the whole sentence. We can look at consensus-based image description evaluation or CIDR. Compared with blue, CIDR matrix does not evaluate semantic similarity on the basis of a reference sentence, but a set of sentences with the same meaning. And the limitation similar to the blue score. CIDR is also based on the comparison between two word groups, and the similarity can only be captured at the word level. We can look at the semantic similarity. The semantic information in this matrix is considered from the sentence level due to the sensitivity of verb to polysemy, such as word mouse can be mouse in biology, which is animal, or it could be mouse in machine, which is the computer accessory. The sentence similarity is limited by the pre-trained BERT model, which introduced much resource consumption in the training process, and it makes hard to generalize in other tasks. Age of information-based semantic matrix. The matrix of delay or latency in the classical communication primarily measure the transmission performance without concerning for the content of the packet. On the other hand, age of information matrix are used to quantify the staleness of the information received at the destination. Here, the scheduling schemes based on the age of information minimization can highlight the importance of the freshness of the data packet and filter out the irrelevant or less important packets given the bandwidth constraint. Here we can look at the combination of semantic matrix. If we have age of information error-based combined with the error-based matrix, so we can look at the error penalty function. In the error-based, the penalty will be high if the state x hat is not equal to the state at the receiver xt. So, but it will be zero penalty if the state is already the same. On the other hand, the age of information penalty function keep increasing linearly unless the packet is transmitted from the source to the destination. So if we combine them together, the penalty of AOII matrix will increase linearly or exponentially only if when the state at the source and at the destination is not the same. So the age of information at query can be another component. So it can integrate the value of information into the age of information-based system. The value of information-based semantic matrix. It measures the benefit of data to be transmitted for the communication goal, which consider not only the content of the data itself, such as burst, exception, etc., but in the monitoring system, there could be the cost of the transmission that need to be optimized. So the value of information matrix are better fit for the goal-oriented communication than the error-based matrix, and therefore it is more suitable for effectiveness level. The definition of value of information, however, is depend on the task, and it is quite difficult to give deterministic explicit function for the value of information. In this example, we can look at the value of information from the freshness perspective, value perspective, relevance, and priority. So the data can be collected from different sources, sensors, variable, or even the mobile media, social media. So they need to go through the packetization and the channel encoding. The semantic information will be transferred to semantic scheduler to transfer the different packet to the different applications such as monitoring and actuation control, social network application. So the semantic scheduler need to take care of the flow level control, caching, resource allocation, and hierarchical network control. We can look at edge-enabled semantic communication framework. From classical communication, where we perform the transmission before understanding, by using shared knowledge background and computational costly operation for semantic extraction, model training, and inference, we are able to move to the semantic communication that convey the understanding before transmission. In order to deploy the semantic communication, we can look at the different layer of semantic extraction method. We can have the cloud layer where the knowledge graph represent the background knowledge. The knowledge graph can compose of the different points, the different edges and nodes to represent the different use cases. So the different use cases can have the different communication goal and semantic information that can be connected through the graph. And the semantic and the edge layer that perform the model application, training, and the knowledge set for caching. So the device layer, we can perform the training, broadcasting, inference, evaluation, uploading, and updating of the semantic extraction model, training, application, and the knowledge building. However, there are the different challenges due to the limited computing power and energy constraint of the end devices could result in long latency in machine learning model training for the semantic extraction and the updating process, therefore degrading communication reliability. The second challenge is the comprehensive knowledge sharing among end device to improve semantic extraction model is at the cost of bandwidth and privacy. On the other hand, incomplete knowledge set will reduce the generalization capabilities of the AI-based semantic extraction. The next challenge is that most semantic extraction methods are task-specific and they are trained separately, which is far from the brain-like cognition and is computationally inefficient due to the redundant work. We can look at the solution in terms of the federated learning enabled semantic extraction. We try to solve the long latency in training, low communication reliability, high bandwidth consumption for knowledge sharing, data security and privacy, as well as the weak generalization capability. By combining the federated learning and edge computing architecture together, we can capitalize on the benefit of them. So for the edge, we provide the proximity to end user, powerful computation and caching capability for background knowledge, storage, sharing, and semantic extraction model training. Edge computing can provide authoritative intermediary for knowledge sharing. Federated learning offers the trained semantic extraction model parameter at the edge server. So this can be exchanged directly with the other edge server with identical tasks. It will accelerate the training process, improving the generalization performance of the model, and of course it can preserve the privacy because in federated learning, only the model parameter will be exchanged, but not the raw data themselves. With the edge computing and federated learning enable semantic communication, so we can look at the steps as follows. First, the edge servers perform the pre-training or fine-tuning of specific semantic extraction tasks based on each communication group channel background knowledge. Then the model parameter exchange and federated machine learning model aggregation are executed over the separate communication group with the same communication goals, but not a shared knowledge background. This is done at the edge server. The derived global model are then broadcast separately to each communication group over the access point or base station. Next, the source devices generate the raw data, and the destination device will receive the semantic information. Accordingly, the semantic extraction model is utilized to encode and decode the semantic information. This is done by end device. Again, the end device, which is the destination, will evaluate the accuracy of the semantic information during the communication for data labeling. Next step, the new label data semantic information and all corresponding raw data are uploaded to the edge server, again through the wireless access point or base station. And in the next step, the edge server perform regular updates for the knowledge set according to uploaded information and raw data for fine-tuning of the semantic extraction model by the edge server. Now we try to address the next challenge that most semantic extraction methods are task-specific and they are trained separately, which is computationally inefficient due to the redundant work. Here we can utilize the knowledge graph. Knowledge graph in semantic communication is composed of source information, goal of the task, and the possible way of reasoning that can be understood, recognized, and learned by all communication parties. The structure of the knowledge graph is much more fixed than that of having to recreate separate semantic extraction model for various tasks. Once the knowledge graph is constructed, it can be cached at the edge server to facilitate efficient semantic extraction method. The first example, we can use the feature map-based semantic extraction with explainable convolutional neural network. Here we store the important weights of all feature maps for the task with the different identification target in the knowledge graph. Another example, the semantic extraction model training for similar tasks can be done with the transfer learning. Here we record the relationship between similar features of different tasks and the related communication goal initialization of the semantic extraction model. For example, we look at communication for collision avoidance application. Task A, the autonomous vehicle can learn how to avoid collision. The autonomous vehicle built the pre-trained model that can be extracted into the knowledge. The same knowledge can be used to build the new model for task B of the collision avoidance of the UAV, autonomous unmanned aerial vehicles. So this is how the knowledge graph can be utilized and transferred among the different applications. Semantic aware edge intelligence. There are many well-studied deep learning models that can be deployed at the end devices to enable the intelligentization of edge network. However, deep learning model optimization comes at the cost of bandwidth and energy resources. The situation becomes worse due to the rapid growth of edge intelligence network. Here we have the main challenges. Deep learning model optimization costs a lot of bandwidth and resource energy consumption. In smart services, intelligent agents are limited to the environment where they are deployed. The monotonous experience results in overfitting issue, long convergence time, and suboptimal performance of the deep learning model. High communication overhead incurred for the sharing and exchange of model parameter and policy. Therefore, we need to look for alternative technology that form the deep learning. We can look at deep reinforcement learning, which is one of the promising methods to enable intelligent agents to perform the semantic extraction and semantic aware edge intelligence. In deep reinforcement learning, each intelligent agent will learn an optimal policy for real-time decision making and, of course, dynamic over the stochastic environment. For example, deep reinforcement learning has shown success in developing navigation system of unmanned aerial vehicle and also for effective semantic extraction in semantic communication. However, the performance of deep reinforcement learning still limited by the monotonous experience, where this issue can be solved through the use of multi-agent and collaborative deep reinforcement learning. This collaborative deep reinforcement learning allows agents to learn an optimal policy, for example, the semantic extraction collaboratively by exchange their model parameter of policy across the cluster of intelligent agents. For semantic aware edge intelligence, we can look at the semantic aware intelligent agent. Not all source agents can be selected for training due to the limited bandwidth and energy supply. Therefore, the bandwidth allocation and the agent performance are often jointly optimized to maximize the utility of the bandwidth. However, it is challenging to filter the helpful source agent because the agent, which can be the mobile device, have different environment, tasks, and action spaces. So this paper, The Age of Incorrect Information, proposed to consider both structural similarity and semantic relatedness when selecting the source agent to perform the semantic extraction. So the structural similarity can be measured by the cosine similarity between the agent model parameters. There is a weakness that it cannot capture the similarity of the underlying task of the agent. Here, agents with similar model structure may not share similar tasks, which is due to the poor collaboration. To obtain the semantic relatedness here, the target agent is trained for a fixed number of steps under the policy of the source agent. The average return value is taken as the semantic relatedness. So here, the multiple agents will be able to share the model parameters for the semantic extraction, where the quality of the shared model is measured by the structural similarity and semantic relatedness. We can look at semantic aware distributed deep learning at wireless edge network. Here the challenge is due to the high communication overhead due to the sharing and exchange of model parameter and policy. So finding the efficient way to compress the model parameter is another alternative essential option to reduce the communication overhead. We can look at one example of gradient model parameter compression. Instead of random sparsification, some study propose to consider the semantic or importance of the parameter during the data or model compression. For example, in this paper, sparse binary compression proposed to drop the gradient with the low magnitude and transmit the gradient with the high magnitude to the edge server. The magnitude of the gradient signifies the importance of the gradient, and that means the higher gradient can represent more important weight of the update. The gradient estimates are specified at the transmitter and only position of the non-zero elements are sent to the receiver. Here, to identify the importance parameter, the paper model pruning adopts adaptive model pruning, where the importance of the model parameters are measured by their contribution to the feature. Next, we move on to the case study, resource allocation for the convergence of semantic communication and edge intelligence. We look at the semantic aware distributed deep learning and the wireless edge network. From the conventional communication system where we consider the communication in efficiency in terms of reducing BER or SER, most existing resource allocation frameworks are designed to maximize the throughput. But here we consider the semantic importance of the bit flow and the semantic aware resource allocation to maximize the semantic performance is proposed. Again, here semantic communication aims to transmit the data or information relevant to the transmission goal of the receiver. And it is necessary to redesign the resource allocation policy. So this is the work from our paper, Economics of Semantic Communication System in Wireless Power Internet of Things. We look at the system model. The system model consists of energy-constrained IoT devices which harvest energy wirelessly for the purpose of text transmission. Different from existing studies that maximize the bit transmission rate, our proposed framework aims to maximize the semantic performance of the system. Here we consider a wireless power communication network where there are a hybrid access point and multiple wireless power IoT devices. So the IoT devices are equipped with semantic encoder, decoder to extract and to reconstruct the semantic information of the text data. For example, semantic information of a sentence with 32 words can be encoded as a two-dimensional matrix with the size of 32 times 16, where 16 here is the number of output dimensions of the semantic feature. So the problem statement here is the hybrid access point can transmit energy to only one IoT device at a specific time. Here we try to answer the question, how do the hybrid access point design the receiver of the energy that will use the energy to transfer the semantic information. Here we develop the semantic aware option mechanism. In the first step, the IoT devices will submit the bit for the energy to the hybrid access point. The hybrid access point will determine which device will be the winner and the price. That means how much energy the access point will transfer to that IoT device. Then the hybrid access point transfer energy, and the next step, the IoT device, after receiving the energy, will transfer the semantic information to the hybrid access point. Now the next question is how to design the bit value. Based on the receivable energy, IoT devices can achieve different semantic performance. Generally, higher energy will result in better semantic performance. Feature output dimension is reduced here when energy received is not enough to transmit all semantic features. So how to design the winner and payment? We develop the deep learning based option to maximize the revenue of the hybrid access point. So the option model based on machine learning can attain the properties of incentive compatibility and individual rationality. The algorithm based on the deep learning is shown briefly in this slide. We look at the performance metric similarity score that measure the sentence similarity semantically. Blue score to measure the exact matching of words in the recovered sentence. Both score decrease when the output dimension decrease. So IoT device will value the energy based on the achievable semantic performance, which is the weighted sum of the similarity score and the blue score. So the performance here show that when we have more output dimension, for example, the more energy that we receive from the hybrid access point will result in the better semantic performance, including the similarity score and blue score. So some of the results, the winner and prize are determined by the deep learning-based auction mechanism to maximize the revenue. So here the results show that the deep learning-based auction mechanism achieve higher revenue compared to the traditional second price auction. And by maximizing the revenue of hybrid access point, the price paid by the winning IoT device is also maximized. Here the energy is delivered to the IoT device that value the device the most to ensure the effective semantic communication environment. Again, the deep learning-based auction mechanism as expected achieve the property of individual rationality and incentive compatibility. So this figure shows the increased wireless energy harvesting time. So this will increase the performance of the semantic communication. And we can show that when the distance is varied, the average bit of the device decreases because when they are far away from the hybrid access point, they need more energy and thus reduce the valuation of the IoT device in delivering semantic information. Now we look at the case study, performance optimization for semantic communication and attention-based reinforcement learning approach. In the system model, we consider a cellular network in which a base station transmits the meaning of text data to totally new users using semantic communication technique. So we look at the semantic information extraction, semantic information transmission, text recover, and then performance evaluation. So we look at the downlink transmission of the semantic information extracted from the original text and transfer the semantic information to the user. User will perform the text recovery. The semantic information of a text data is modeled by a knowledge graph. Here we have the entity and relation. So the entity provides the recognition of the words and relation provide the classification among the words. So we have entity, relation, relate to the entity. So we have the original text. We are able to use the semantic extraction algorithm to construct the knowledge graph. Given the transmission delay threshold, the base station must select the partial semantic information. So here we look at the stochastic lexicon model used for speech recognizer. So we can have the data rate depends on the resource allocation for each user to be the example here. So at the text recovery, each user recover the original text by using graph-to-text generation. Say we have a partial semantic information represented by the knowledge graph. We apply the semantic inference engine to reconstruct the text or to recover the text so that we can evaluate the performance of the semantic communication. Here for the semantic information matrix, we look at 3 matrices, including the semantic accuracy of the recovered text. We look at the semantic completeness and the matrix of semantic similarity. So the different performance matrices are combined together. So the accuracy ensures that the meaning of the words can be retained at the receiver. Completeness indicates that the receiver can receive as much as semantic information. And the metrics of semantic similarity look at the similarity of the recovered text compared with the original text. Then the optimization is formulated. We look at the total matrix of semantic similarity maximization problem. So E is the total matrix which depends on resource allocation and semantic information selection. So they need to be done jointly. Here, the question is how to build the relationship between non-mathematical optimization variables and the objective function. The objective function here is calculated based on the text recovery model. So there is no closed form solution. And we need to evaluate the importance of the semantic triplet. We look at the attention relay reinforcement learning for semantic information selection and resource allocation jointly. The importance distribution of the semantic information is determined by the attention value. Here the attention value is determined by the network of attention reinforcement learning. We have the input layer connected to the hidden layer and provide the output with the softmax layer. We apply the attention policy gradient algorithm. So the components of the attention policy gradient include the agent, which is the base station, and the action include the semantic information to be transmitted, and the partial semantic information to be transmitted depends on the constraint of the delay threshold and the semantic information requirement. So here we define the theta, which is the parameter of a deep neural network to map the input importance distribution and the output resource allocation. For the simulation result, we have the original text, and then we extract the original text into the knowledge graph, and the recovered text can be obtained as shown in this example. We compare with two baselines, which are randomly selecting the semantic triplets and directly transmit the original text. Our proposed algorithm can improve the semantic information performance. And the convergence is quickly to the optimal solution. Now we can look at the future directions of the semantic communications research. Interpretability and explainability of semantic communication can be investigated, as unexpected information often appears in communication. The black box nature of semantic extraction method may hinder the implementation. Therefore, interpretability in semantic extraction need to be studied to associate possible causes and results and to guide the improvement to the semantic extraction model. Also, the semantic noise privacy preserving need to be considered. For the communication group with a similar background knowledge and communication group, the eavesdropping becomes much easier. Consider the use of the covert communication in which the artificial noise can be used to secure the wireless transmission. Covert semantic communication can be one of the research direction. We can look at the variable length semantic encoding. Existing word merely consider the dynamic channel gain in semantic extraction without looking at the resource constraint. But this problem becomes challenging in multi-user scenario in which the resource availability can fluctuate, such as the available spectrum and transmit power. So we need to evaluate how this dynamic behavior can be optimized in the semantic communication environment. Deep learning-based semantic extraction for task similarity can be considered for the semantic relatedness between multiple transmitter agents. So we can use the deep learning network to extract and construct the model parameter so that they can output the embedding as the semantic representation. And finally, we can look at the semantic compression of the model parameter to reduce the transmitted data further. Thank you very much for your attention. And if you have any question, please feel free to send me the email at dniyato@ntu.edu.st. Thank you again.